Welcome to the live session of Basic Linear Algebra week 8. So in this session we'll be discussing about the abstract vector spaces. So let's start with some simple questions. So let's take a simple question first. In R2, you have a line through origin. Say for example, such that y is equal to 3x. Then let me know if this is a vector space or not. Okay, so vector space means so we have seen this already also in previous sessions. So vector space means we must have definitely a zero vector must be there. So we must definitely have we have three conditions. Zero vector should be there, and addition should be satisfied, and also the scalar multiplication property that should be satisfied. So we see here that we have a line xy with y is equal to 3x. So if we have x is equal to 0, then y also will be equal to 0. So 0 vector is satisfied. And if you see the addition, then x1 plus, so must have like if we see this, we can write this as we can write even like this. So which means that we can get in the individual forms. Addition also will be satisfied, and the scalar multiplication if we see, then even this thing will be satisfied. So it will be like alpha into x and alpha into y, and we have y is equal to 3x condition, and if we say that 3 alpha x will be equals to alpha y, so even this condition is satisfied for scalar multiplication. So the given line through origin, that is going to be the vector space. Okay, so take one true or false question. The set 2 by 2 of 2 by 2 matrix with real number entities is not a vector space. So tell this is true or false.
False. It is a vector space.
Yeah, so it's a vector space. So for example, if you take that A, B, C, D as some 2 by 2 matrix, and if you add some other matrix to it. So addition will be satisfied here. So addition will be satisfied as we know. So this is going to be the vector space. And even if you do multiplication, then that will be for individual element. So this and also 0 is possible. So if all the things are 0, all the numbers a, b, c, d are 0, that's the real numbers only. So it's all the three conditions are satisfied, and it's going to be a vector space, and so there's going to be a false. This is a false statement. Okay. So if you are given a cos theta plus b sin theta, so this is a vector space or not? So this function in terms of theta, is it does it form vector space or not?
What is the question? Like a space of containing all functions like this.
Yeah. So you the hint. So the thing is, you must be able to write.
It is. It is not a vector space, I guess.
It's not a vector space. Okay. So
Hmm. So you're saying that okay.
so you must check. Okay. So theta. So you must check that this is satisfying, and so you just check that this is satisfying or not. So suppose if I take f1 of theta as a1 cos theta plus b1 sin theta, and f2 of theta as a uh, okay, a2 cos theta and b2 sin theta, then f1 plus f2 of theta can be written as basically I'm saying that f1 is having a1 b1 and f2 is having a2 b2. Then we can write this one as a1 plus a2 cos theta and b1 plus b2 sin theta, and which means that a1 cos theta plus b1 sin theta, and we can split this as a2 cos theta plus b2 sin theta. Then this is nothing but f1 of theta and f2 of theta. So f1 plus f2 of theta can be written as this way, and also that I have to check whether this condition satisfies or not. So even this will satisfy. So if I say r, so will be so if so f we have a and b. So rf will be having ra and rb. So which means that ra cos theta plus rb sin theta. I can write as a cos theta plus b sin theta. So which means that rf theta is equals to r f theta. So even this condition is satisfied. So this is this forms vector space. The given function forms a vector space. Okay, take on one more question. with b square f by bx square plus f is equal to 0. So does this form a vector space? So you just have to see that you have two functions f and g, and you have to check whether f of the addition you can write
Yes,
it
it
as,
is forming a vector space.
yeah. So yeah, it is on a vector space. That's right. So you have to check these two conditions. So for this, so b square of f plus g by dx square plus f plus g is equal to 0. So you can write it as b square f by dx square plus b square g by dx square plus f plus g is equal to 0, and b square f by dx square plus f plus b square g by dx square plus g is equal to 0. So f of x plus g of x is equal to f of equal to 0. So that satisfies. Now if you see this, then b square by dx square r of f plus r of f is equal to 0. So you can pull r out. So even this satisfies. So this is a vector space. So if I change the question slightly, saying that this is not 0, this is not 0, this is 1, for example, then
Then it is not a vector space because zero function is not there.
yeah, it's not a vector space. Yeah, so zero vector is not there. Yeah, so it's not going to be a vector space. And even if you check the addition and multiplication, even that won't be satisfying. So so if you have addition won't be satisfying here. So if you see here that let's go to the next slide. Is equal to 1. So if I do so if I replace f with f plus g, then I'll be getting as d square f plus g by dx square plus f plus g, that should be 1. But when you have that d square f plus d square f by dx square plus f is equal to 1, and d square f by g by dx square plus g is equal to 1. So when you add it, you'll be getting as d square f by dx square plus d square g by dx square plus f plus g as 2. But when you bring it in this form, you'll be getting as 1, which is 2. So it's not possible. So it's not a vector space. Okay. Take just a simple question. So you have a function 3e power x minus 2e power minus 6. Then what is the additive inverse of this? So what what is the additive inverse? So when you add something to this, you must get 0. And what is that something? That is, that's called additive inverse. That's an hint here. Yeah, so it's a simple question. Please don't think so much on this. So this is 3 power x minus 2 power e power minus x. So I'm adding some function g to it so that I'm getting 0. So that's just going to be a simple negative of this. Yeah, so just a negative. Yeah, so someone answered this. So it's going to be negative of this. So that's the additive inverse.
Negative. Negative.
So check if the given one is vector space or not in R3 space. So you have x, y, z in R3 such that x plus y plus z is equal to 1. Check this is vector space or not. Yes or no?
No, again, zero vector is not there,
Yeah,
so
so when you
you
put
can say
0,
that.
0, 0, then so 0 is equal to 1, that's absurd, so it's not going to be a vector space. And even if you check the additive inverse, then if you just do that x1 plus x2, y1 plus y2 and z1 plus z2. Okay, so let's do in this way. So x1 can be written as 1 minus y1 minus z1, and x2 can be written as 1 minus y2 minus z2, and x1 plus x2, it should be 1 minus y1 plus y2 minus z1 plus z2, but from these two things, if you just add them, then you'll be getting 2 minus y1 plus y2 minus z1 plus z2. So that's not same, so it's not going to be vector space. So similarly check. So let's take up simple questions like this so that we'll get used to the concepts at least in the starting. Okay, so this one is a vector space or not?
Yes, it is a vector space.
Yeah, so first of all 0 is possible because 0, this relation will be satisfied. 0 plus 0 minus 0 plus 0 will be equal to 0, so okay. And then even if you take x1 is equal to, then z1 minus y1 minus w1, and x2 is going to be z2 minus y1 minus w2, and if you add them, you'll be getting z1 plus so actually you must get this one, and you will get this one. um, okay, so you will get this one from even this relation, so that's going to be a vector space. Okay, so let me know this one, whether this will be vector space or not. So question is, in R3 such that x square plus y square plus z square is equal to 1.
Not a vector space,
So first of
actually,
all, 0
for
if
the
you see,
same reason.
so 0 if you see, it's not going to be, first of all, here it's gone, and addition also, if you see, x1 square, you'll be getting as 1 minus y1 square, sorry, minus z1 square, and x2 square should be 1 minus y2 square minus v2 square, and here you must be having x1 plus x2 the whole square must be equals to 1 minus y1 plus y2 the whole square minus z1 plus z2 the whole square, and clearly you will be getting x1 plus x2 the whole square plus 2x1 x2 is equal to 1 minus the whole thing will be getting, and clearly you can see that it's not going to get satisfied. So if you put them here, then you're not going to get it. So you'll be getting something at the end as 2x1 x2 is equal to 1 minus 1 minus 2y1 y2, something you'll be getting like this. So addition is not satisfied here, so, and also 0 vector is not enclosed, so it's not going to be vector space. Okay, so you have this matrix such that A, B, C belongs to real numbers. Then this forms a vector space or not.
Not a vector space, actually.
Yeah, it won't be a vector space. So first of all, if you're writing, okay, so multiplication, if you are seeing, so, okay, first of all, there is 1 here, so you won't be getting 0 0 0 0 here, so it's not going, first of all, that fail. And if you see that but scalar multiplication, if you see, then definitely you can get it out. So scalar multiplication will be satisfied, but but if you do this, that won't be equal to, so it's not a vector space. Okay, so one more question. Xy belongs to real numbers, and such that conditions are 3y is equal to 4, and 2x minus y is equal to 3, and also 6x plus 4y is equal to 10. Oh, I'm not audible? Oh god, I'm not audible. Oh, sorry, I muted somehow. I don't know how it happened. I'm sorry. Did I miss something? Where did I miss? Okay, so I think I was here. So first of all, the scalar multiplication here will be satisfied. Scalar multiplication, though it is satisfied, but in this case, if you add, so this is not going to be equal, so that's not a vector space. So now tell me, this is a vector space or not? This question is here. So did I miss anything? Did I let me know?
No,
Yeah, so
nothing you missed.
yeah, so this is the conditions you are given for xy vector space. So let me know whether this forms.
Not a vector space. Yeah. Nothing already discussed.
Yeah, first of all, these conditions, if you check closely, 2x minus y is equal to 3. Then suppose if I am adding this, then I will getting 3x plus 2y is equal to 7, and I have this condition here that 6x plus 4y is equal to 10. So if I'm suppose multiplying by 2, then it's going to be 6x plus 4y is equal to 14, and which is not equal to 10 here, right? So 14 is not equal to 10. So first of all, these conditions, no, they are not in such a way that so you get a vector space first of all, and even the zero vector is not going to be is not in this. It won't contain the zero vector even. So it's not a vector space. So now you have such that a0 minus 2a1 is equal to 0. So we come to polynomials.
And here we should check x and y, x plus y, or a naught.
Yeah, someone is saying something. I'm not
Yeah,
able to.
someone is saying something.
Someone was saying something.
And here we should check x plus y.
Volume is very low.
or
Who is talking? And I think. Okay, so let's see this. Somehow, okay, somehow I went out of the meeting. Okay, so we'll take, suppose I'm taking that, so I'm having this, such that a0 minus 2a1 is equal to 0, and also I'm taking one more vector as b0 plus b1x, such that b0 minus 2 b1 is equal to 0. Then if I'm adding it, then a0 plus b0 and a1 plus b1 of x, we can write, we will be getting as a0 plus a1x and b0 plus b1x. So you are able to write this in this form. And also the scalar multiplication. You can get in this way. And even the conditions, if you see, then a0 plus b0 minus 2 of a1 plus b1, that is going to be 0 from these two conditions. So that's going to be this is going to be satisfied. So this is going to be a vector space. Okay, now you have one more question, last question in this area. Okay, so this one, does it form vector space or not? even, yeah, 0 vector is there here, and also if you write as x1 plus x2, x1 plus x2 plus y1 plus y2, x1 plus x2 plus y1 plus y2, and y1 plus y2, you can write as individual matrices. You can split this. Okay, that's there, and even the multiplication, scalar multiplication is satisfied here, so that will be vector space. So take up next question. Okay, so which of these are members of the span in a vector space of real valued functions? Of one variable, of one real variable. So I will give you some so real functions in one real variable. So one real variable is x, and real functions f is a real function. So so you have functions here. So which one will span? Which one will be spanned by this one? Whatever vectors I gave here. So which of these four functions will be spanned by cos x, cos square x, comma sin square x? Is the question clear, first of all? If no, kindly ask.
A and D.
A and D are okay. So A and D, yeah. So the vector space spanned by cos square x, sin square x will be in the form of the linear combination b sin square x. So this is the function. So one is for A it is 1. So if A is 1 and B is 1, then definitely you can get on right hand side 1. So yeah, so this is going to be spanned by cos square x and sin square x. And if you see for this, so you probably won't be able to solve and find A and B such that will get this. So this is not spanned by the cos square x and sin square x. So and if you see sin x, even for this, so they are going to be independent. So you are not going to get so all these things are so you are not going to get this. So you cannot find A and B. So cos square x, sin square x, and sin x are independent. So you cannot get it from the linear combinations. And but if you see this cos square x, a cos x plus b sin square x is equal to cos 2x. So which means that cos square x minus sin square x. So if a is 1 and b is minus 1, then you can get this. So this will span. So a and b will be spanned. A and b. So these two functions will be spanned by given basis, but the other two is not. Are not going to do. Okay. So to find next question, find basis for the quadratic polynomial such that P7 will be 0. So what you can do here is you have a quadratic polynomial, so you can write in this way. So this is your P2. Then P of 7, meaning x is 7. So you'll be getting a 7b plus 49c is equal to 0, because P7 is equal to 0. P of 7 is given as 0. Then from this you can write a as minus 7b minus 49c, and the polynomial a plus bx plus cx squared you can write as minus 7b minus 49c plus bx plus cx squared. So you can take b out and you'll be getting minus 7 plus x, and you'll be getting x square minus 49. So the given polynomial with p of 7 is equal to 0 can be written in this form. So you can write in this linear combination of minus 7 plus x and x square minus 49. So these two are bases. So this is the basis for the given quadratic polynomial. Is it clear? Okay. So take next question. Such that.
मैम
Yeah.
प्रीवियस क्वेश्चन रिपीट करें.
Yeah. What do you want?
Repeat the previous question.
Okay. So first of all, you are given a quadratic polynomial such that p of 7 is equal to 0. So that is the condition given. So quadratic polynomial means you'll be getting this. Okay. So I am giving that p of 7 is equal to 0. So when I am substituting x is equal to 7, so I am getting that a plus 7, b into 7, which is 7b, plus c into 7 square, which is 49. So I am getting this one. Okay. So now I am writing that a in terms of b and c. So minus 7, a is equal to minus 7 minus 49c. Okay. So now this polynomial I can write as minus 7b minus 49c, because a I got like this. Instead of a I am writing like this, plus bx plus cx square. Okay. So now I am taking b outside the whole thing. So b is there in this term and this term. So b minus 7 plus x plus c, x square term is here and minus 49 is there. Okay. So this polynomial with this condition I am able to write in the linear combination of minus 7 plus x square minus 49. I asked for basis, right? So with these two things I can get any polynomial, quadratic polynomial which satisfy this condition. So this is the basis. Dimension is 2. Is it okay?
Yes, ma'am.
Yeah. So take up the next question. So you have this condition. So find the basis for this.
Ma'am,
Yeah.
ma'am, if for the previous same question, if P of 4 is equal to 0,
If P of 4 is equal to 0.
then can we say the basis are minus 4 plus x, comma, x square minus 16.
Yes, that will happen. Yes.
Okay, thank
Yeah,
you.
because it will be like a plus 4b plus, yeah, the same thing, no? The number itself and the square, no? In this
Yes, ma'am,
case.
thank you.
So we'll be getting a similar way. Yeah, so find the basis for the matrix such that these conditions are satisfied. Okay. So let's do it in this.
So it is getting as half. First row is half.
Yeah.
First row is half minus 1 by 6, 1, 0.
Sorry.
Half. First entry is half.
First entry is
Half, 1 by 2.
half. Okay.
Then second entry, first row, second minus 1 by 6. Then second row is 1, 0.
This
Another one is half minus 1 by 6, means same. First row is same. Second row is 0 and 1.
Okay, so basis, it's as we saw already, it's not going to be unique. So okay, so I might have solved in some other way. Okay, so let's see this. Okay, so we'll check once. Okay, so can we get it by the linear combination of this? Okay, then once we'll check. We'll just check. Okay, so A is equal to, so we got that. Okay, so we have A, B, C, D, and we have conditions 2A minus C minus D is equal to 0. A plus 3B is equal to 0. So I can write A as minus 3B, and so that's why in 2A, in this condition 2A, I can write as this minus C minus D is equal to 0. So minus 6B minus C minus D is equal to 0. So D is going to be minus minus 6B minus C. So here I am replacing terms. A I am saying as minus 3B, B, C I am saying C, keep it like this, and D will be minus 6B minus C. So this I can write it as b minus 3 1 0 minus 6, and I can write in this way, right? So this will be the basis. But having said that, okay, so as you said this one, let's check once. 1 by 2 minus 1 by 6 1 0, and the first column is same, and this two are interchanged, huh? Yeah, so can we get from this? Okay. So is this satisfying these conditions, these two conditions? So b is equal to 1 is equal to yeah, so it's satisfying. Yeah, so even this can be basis. Yeah. So is it clear? So basis can be basis is not unique, so you can find anything. So the dimension you have here is 2. So can I proceed to next question?
Yes, please.
So I did it in this way, so I got like this, but maybe you might have solved this in some other way, and you could have gotten some other things. So, but it's so whatever elements are there, they're satisfying the conditions. So I'm saying that it's that's also the basis. Okay. So the true or false question. Okay. So think and tell for any subset S of a vector space, the span of the span equals the span.
Yes, true.
True, ma'am.
True. Yeah. So if you have S is a subset of vector space, then span means whatever basis you are having for that, all the linear combinations you are doing, that is called whatever you are having S in S, and you are doing the linear combinations, you are going to get. Okay, first of all, let's write in mathematical form. The span of span equals the span. Okay, so we have to see whether this is true or not. So you have some vectors in S, and if you are adding it, that is called the span. By the linear combination, you are going to get the span. For this, again, you are doing this. Again, you can you can just understand from this that if you have some things like A and B, and I'm able to write some as a combination. I don't know how to tell this. Okay. Okay, so you are having okay, so you are having the okay, so such that okay, so this is suppose the basis for S, and whatever linear combinations you can do for this thing, that is a span of S. And if you are so this is going to be linear combination. So span is going to be linear combination of this, and span of span is also going to be the linear combination of this only, right? So both will span the same thing. So you'll be getting, so this is going to be true. Is there any doubt in this? So you can get the linear, so basically these two things will be having the same span. Because it's just a linear combination. So whatever basis you are having for S, then if you're doing the linear combinations, you're going to get the span of S. And if you are doing this, if you are still again doing the linear combinations of again the span of S, then again you can somehow get it again with the linear combination of the basic basis. So the span is going to be the same. So it's going to be true.
Ma'am, it will be easier if you explain with R3.
Sorry?
This will be more easier if you explain with R3.
It will be more easier if I explain with R3. That's what
Yes,
you're saying? Okay, for example, if I have a vector space R3 and suppose I'm having that like this. Okay, so suppose I'm taking the linear combination like this. So that is span of S. So if S I'm having such that basis is these three things, then the span of S will be the linear combination of the basis. So I'm going to get the linear combination of what I have in S. So that is I'm going to get it like this. So this is a span. Okay. So now suppose if I'm saying that okay, suppose I'm taking like this. B1. So this is in the span of S. Agreed, no? So this is in the span of S. Similarly, if I'm doing for A2, B2 and C2, that is also in the span of S. So like that they can be many things.
But the statement
For
says
this,
span
if
of
I'm
the
doing
span.
yeah.
But the statement says span of the span.
Yeah. So that's what I'm saying. So so if I'm taking the linear combination of, for example, I'm saying this as some 1, if I'm saying this as 2, and if I'm saying this as 3, okay, so if I'm doing like this equation I'm telling like that, I can still express in the linear combination of this, right? Some alpha, some linear combination of this. That's what I'm trying to say.
Yes, ma'am.
You are understanding?
Yes.
So span of span will again come to this only, right? So even this will be in the span of S. So that's the true statement. Did I convince you? Yeah? So what I'm trying to say here is span means the linear combination of whatever you have there. Okay.
Yes, ma'am.
Yeah, I'm not able to hear anything. Is it okay?
Yes, ma'am.
Yeah, so span means the linear combination. So suppose if I'm having like this, okay, so span means linear combination, okay, but now I can have so many things in this. But if I'm taking the span again of this, I can again write as again the basic thing, whatever I took the starting. So I can write as a linear combination. So the span of span is going to be span. So that's the true statement, okay? Okay, so let's take up another question. Again, a true or false question. If A, B are subspaces, so think and tell this. We have some true or false questions which you have to think and then answer. Of vector space their intersection A intersection B must be a subspace. So this is the question.
True, ma'am.
Yeah, so why so? Yeah, could you explain?
Yeah, so we can take some vectors v1 and v2 both from A intersection B. Then v1 plus v2 belongs to A.
So first of all, how do you
And again,
how do you say that that is a subspace? First of all, what conditions to check that it's a subspace?
you're not audible at all.
Yeah. So first of all, what conditions did you what conditions has to be satisfied for anything to be subspace?
Alpha v1 plus beta v2 belongs to the
So
intersection.
first of all, yeah. So zero vector must be there. Anyways, that we know already. Zero vector must be there, and closed under addition, and also closed under multiplication, scalar multiplication. Okay, so yeah, so suppose if you have a vector space V where A and B are subspaces, then A is a subspace, or A is a subspace as in the question, and B is also a subspace. So which means that I am telling that A has a zero vector and also B has a zero vector. So whatever so this intersection cannot be empty, right? So definitely the zero vector will be there in the intersection, because A is a subspace and B is a subspace, and subspace means A has a zero vector and even B has a zero vector. So the intersection, no, at least it will have a zero vector. So definitely there will be a zero vector. Okay, so yeah, so zero, so this condition is satisfied. Okay, so next we'll see this thing. Okay, so suppose I'm saying that u and v are vectors in A intersection B. It means that u is a vector in A also, and u one second. So I'm saying that u and v are in intersection A and B. It means that u and v will belong to A, and u and v will belong to B also, right? Suppose if I am saying that two vectors u and v, such that they are in A intersection B, it means that u and v belongs to A also, and u and v belongs to B also. And I said that A and B are subspaces. Okay, so u plus v will belong to A, and u plus v will belong to B also. Okay, so which means that again u plus is common, so it's going to be in intersection. Okay, so the addition is closed. So if you have any vectors u and v in A intersection B, then even the u plus v also will be in intersection of A and B. Okay, so addition property is satisfied here. Clear? Any doubt? Student, shall I move for? Can I go?
Yes, ma'am.
Yeah, because I'm saying that u and v, I'm just taking some vectors which are saying that u and v are in A and B. Okay, so intersection means u and v will be in A also. It's somewhere here means. then it's going to be in A also, it's going to be in B also, right? So as I said that this A and B are already subspaces, is the question. So definitely if this is the condition, then even U plus A, U plus V should be in A as well as in B. So which means that in intersection that's going to be there. Okay, so addition is closed. Okay. So now let's see about the multiplication. So U belongs to A, and suppose U belongs to B, then RU will belong to A because A is a subspace, and RU will belong to B also, which is because B is a subspace. So RU will belong to A intersection B, okay, because it's there in both. So even multiplication is closed here. So this statement will be true, right?
Yeah, ma'am.
Fine? Yeah. Somehow I'm not able to hear your voice, even if I can hear that, I can sense that you are responding, but I cannot hear it clearly. Is my volume low? Is someone talking? Hmm? Fine. Okay, so similarly take up another question. So similar to whatever we had before. Okay, so this is also true or false question. Network issues is from my end or from your end? Someone said network issues from your side. Okay, fine. So if true or false question again. If A and B are subspace of a vector space, then A union B must be a subspace. True or false? So true means why it is true, and false means what is the correct statement for this, when this can be correct. So someone is saying it's true. Okay. Okay, oh, by the way, this is a false statement.
Yes, ma'am. Yes.
So why it is going to be false is, okay, so first of all, zero vector is there or not? Yeah, A is a subspace, so zero vector is going to be there, and B is also a subspace, so zero vector is going to be there. So A union B will also definitely have zero vector. So that condition is satisfied here. Now we'll see addition is closed or not. So now I'm saying that suppose U is belonging to A union B, and there's a vector V which is belonging to A union B. Okay. So what does this mean? This means that A belongs to, U belongs to A or B. Or maybe both. And V belongs to A or B or maybe both. Okay. So on this cases, okay, so let me write it again. Okay. So let's see some cases here. So for example, U and V belongs to A. Then U plus V will also be in A, right? Which means which means you can say that A union B also. So if it's so if U and V is belonging just to A, is definitely belonging to A, then U plus V belongs to A because A, as I said, is a subspace. Okay, so it will be there in A union B also. Now case 2. Yeah, so what I'm saying, what you're trying to prove ultimately here is if U is so as we did in the previous case, as if U is in A union B and also if V is in A union B, we have to check whether U plus V belongs to A union B or not. If it is true, then it's a true statement, or else it's not. Okay, so case 2, let's suppose if I'm saying that U and V belongs to B, then even U plus V will belong to B, and which means that it belongs to the A union B. Okay, but if the case 3, if you take that U belongs to A and V belongs to B, okay, then can you really comment that U plus V will belong to A union B? There is no guarantee what will happen there. Okay, for example, let's take one counter example for that. For example, A is x comma 0 and B is 0 comma x, for example, and so A union B will be x comma 0 and 0 comma x. Okay, so now suppose I'm taking U vector such that it's in A, and V vector such that it's in B. Now I'm adding both U and V, then I'll be getting 1 comma 1. Okay, so but my A union B is this. Okay, so this does not belong to this, right? So it's a false statement. When this can be true? Only if either one of these is subsets. For example, if A is subset of B or B is subset of A, then A union B will be equals to A, and or for this and A union B for here will become B. Okay, so then in this condition, definitely the union, if A and B are subspaces, then A union B also must be a subspace if one of these are subsets. Else it's not like that. Okay, so similarly take one more question. If A is a subspace of some v, then its complement which is v minus a must be a subspace. True or false?
False.
False?
False.
Why do you think so?
Yes, subspace. Yes, subspace.
Sorry, I can't. I not able to hear your volume at all. Your voice. Yes, so who is trying to answer?
If A is a subspace, then A will have zero vector.
Yeah.
Whereas B minus A don't have zero vector.
Yeah, that's correct. Yeah. So V is a space means definitely there will be a zero vector for V, and if you have A, then A is a subspace I told, so it will also have a zero vector. So V minus A means the zero vector is gone. So zero vector is not there. So here itself you can say that it's not going to be a subspace, so it's going to be a false. And even if you see the addition, whether it is closed or not, then if you take suppose some two vectors which are in complement, then which means that u is not in V, and okay, so small v means the vector and capital V means space. Okay, so what is, let me do it okay, so let me say it in this way. So u1 and u2 are two vectors that in V minus A, then u1 does not belong to V, and also A, sorry, it doesn't belong to A actually, and u2 also does not belong to A. So you cannot really say that whether there's no guarantee that whether this must be in V minus A or not. So it's not, there is no guarantee on that. So for example, if you say that A is x comma 0 and V is, for example, it's R2 space, and A is x minus 0, which means that you are removing the x-axis from here, and you are taking that V1 as 1 comma 1 and U1 as 1 comma 1 and U2 as this way, then U1 plus U2 will be equals to 0 comma 0. So that's not there. So I hope this is clear. Okay, one more true or false question. So if S is a subset of T, and these are vector, and these are subsets of S and T are subsets of vector space. So span of so if okay, so S is a subset of T and both are subsets of vector space, then span of S is subset of span of T. So that's a true or false?
True, ma'am.
Yeah, that's going to be true. Yeah, so we can just analyze this, right? Like for example, if S is a subset of T, so whatever linear combinations of this you are going to do, that's definitely going to be in T. So that's true. Okay, and one more question. If S and T are subsets of vector space, yeah, true or false? Another question. I'm not saying here that S is subset of T. Okay, this is another question.
It's true, ma'am.
Okay. So I'm not saying that S is subset
No,
of
false. It is false because
It is true,
span
ma'am.
of span of S union span of T might not be a vector space.
might not be. Sometimes there might be some cases, but it's not. For example, if you take some examples like S is having and T is then S union T span will be but that is not there, no, in which is not there in, it's not there in this. So this basically we do basically the S union T will be having as only this thing is oh, I'm sorry, just take this example, yeah. Okay, so we have only this as common. Okay, so this don't come in this, so it's not true all the times. So we have some examples where these conditions can be false, so this is going to be false. Okay, so if S, T are subsets of vector space, so basically this will be true definitely when if one is subset. Okay, if either this condition is there, then this is going to be true, else it's not. Okay, so this is true or false? Okay, there are so many questions to go. Okay, so I'll just tell the answer. Okay, so S is okay, suppose for example, so basically this is false actually. So for example, if S is in 1 comma 0 and T is such that it's in this way, then span of S intersection will be span of and 0 comma 1. Okay, and span of S will be span of 1 comma 0, and span of T will be span of 0 comma 1.
Oh, ma'am, S intersection T is phi. Means no common element is there. No?
Sorry.
S intersection T is phi. So it is span of phi.
Okay, so null. Oh yeah, yeah, null set, no? Yeah, null set. So what do you get?
I think it is true actually. I think it is true statement. I feel like.
Okay, so if it is 1 comma 0 and 0 comma 1, it's null set. And okay, let's take one more example. Okay, let's keep this on hold for a while, and let's see in the end. Okay, so take one more question. If span of, raise your hand. Yeah, someone wants to say something? Basically, I think this session may end longer than 2 hours. Sorry, I'm totally not able to hear you. You're trying to say something, Shahid? Shahid Afridi? There will be something to check. Intersection is, yeah, there will be something. Yeah, that's what. So right now I'm not able to think about examples to say this. So let's see some other questions, because if we spend much time in single question, then we might miss other part of whatever I wanted to say. So I'll try to say now, or else if it is I'm not able to say, at least I will try to discuss in the discussion forum, because it's the last class. Okay, so if any doubts we have, or if you have any doubts, maybe then we'll be I'll be discussing in the discussion forum, because this will be the last class. Okay. Span of the complement is equal to the complement of the span. So true or false?
Can you please move the cursor because the question is not.
Yeah, sure. Okay, okay, see, let me tell the answer. So it's basically false. Okay, so see, first of all, let's try to put this in mathematical terms. So complement, so span, okay, span of the complement. So suppose V I have a vector space. Suppose V is a vector space in some Rn. Then and A is a subspace. A is a subspace in that. Then so A is a subspace. Then complement means span of the complement means whatever I removed it, and the span means this, and is equal to complement of the span. Okay. Yeah, complement of the span. Okay, so this is what actually the sentence means. So for example, now let me take okay, so let me take one example saying that suppose V is in R2 space, and suppose I'm taking A as some x-axis, so which means that V minus A, it means that x comma y, where y is not equal to 0, means everything except x-axis. So basically you have R2 space and I'm removing x-axis from that. For example, A I'm taking as x-axis and I'm removing x-axis from that. So everything in R2 space except x-axis. Okay. So now so suppose V is in R2, so I can have V minus A will contain this, right? So is there any I'm just taking an example that V minus A will contain this, so this will satisfy whatever conditions we have, right? So 1 minus so 1 comma 1, so it's there in R2, and it's except x-axis, so it's except this. Okay, so it can contain this thing, right? Okay, so now if I'm saying that this spans V minus A spans okay, so if you do this, you will again get R2 only, right? So V minus A, the span of this will again be R2 itself. Now let's see what is V minus span of A. Okay, so this means that V is R2 anyways, we started with that, and span of this which means that from R2 you have taken x-axis. Okay, I mean fully you have taken the x-axis, so now you will be left only with y-axis. the x component, whatever this thing is there, so suppose it is like x comma y, you are totally removing x from that, so that's going to be just y axis. Okay, so this is just y axis, this line, and this is r2, so these are not same. So the span of the complement is never equal to the complement of the span. Is that okay? Fine. Yeah. Let's take some numerical questions, somewhat easier. Okay, so check. I think this session might go beyond 2 hours. Check if these are linearly independent or dependent. Okay, so I am giving 3x plus 3x square and x plus 2x square and 2 plus 2x plus 2x square and 8 minus 2x plus 5x square. Okay, so whether this will be linearly independent or not. Okay, so we'll see. So I can write this as 8 3 3 0 1 2 2 2 2 and 8 minus 2 5. Okay, so sorry, I can actually transpose all this. So what will be the rank of this? Rank can maximum be 3. Okay, rank can maximum be 3, but you have vectors 4, right? So when there is no full rank, it's going to be dependent, so it's going to be dependent, right? So these are going to be dependent vectors because rank the rank is less than the number of vectors you have. Okay, so let's take next question. F of x is equal to e power x and g of x is equal to ln of x. So this will be linearly independent or not? Linearly dependent or independent? So basically, if you are doing like this constants, then if it is 0, then individually C1 also should be equal to 0 and C2 also has to be 0, right? That is called the linear for if there is C1 C2 for this condition to be satisfied, if and only if C1 and C2 are 0, then that is going to be linearly independent. Okay, so let's see for this case. So for example, if I am taking x is equal to 1, then what I'll be getting? F of x I'll be getting as e, and g of x I'll be getting as 0, right? If x is equal to 1. Some example I'm taking, and suppose if I'm taking x is equal to e, then f of x I'm going to get as e power e, and g of x I'll be getting as 1. Okay, so for this condition, if I check, then c1 e plus c2 0 is going to be 0, and c1 e power e plus c2 1, that is also going to be 0. So if I am trying to solve this two names, if I am trying to solve these things, this will give me c1 e is equal to 0, and this will give me c1 e power e plus c2 is equal to 0. So here from here I'll be getting c1 as 0, and from if I'm substituting here, then I'll be getting c2 also as 0. Okay, so this linear combination will become 0 only if and only if c1 and c2 both are going to be 0. Okay, so that is linearly independent. Fine. Kindly stop me if you have any doubt in this. I'm just going faster. Okay, so now if you have these three things, let me know if these are going to be linearly dependent or not. Or independent. Okay. So yeah, so you'll just check whether coefficients will turn 0 or not if the linear combination is going to be 0. So just take some examples, like for example x is equal to 180 degrees, for example. You take x is equal, then what you will get? You will get as c1, c2 of 180 degrees is going to be 0, and c3 of 360 degrees also is going to be 0. So it's going to be 0. Yeah, someone wants me to go to back page. So what I was trying to explain is, if you want to know whether there is linearly dependent or not, then you will be seeing that linear combination, if it is 0, then the individual coefficients also has to be 0. Okay, so that's one condition you can check to find whether whether it's linearly independent or not. So when you substitute values, some values you are substituting, and then you're trying to find the coefficients, then c1 will be equal to c1, and coefficient both are going to be 0, so that's going to be linearly independent. So next question was this. So now I'll check some values. X is equal to 180 degrees, then I'm getting as c1 as 0, which means c1 as 0, and suppose if I'm taking x as 90 degrees, then I'll be getting as c1 plus c2 is equal to 0, because sin 90 is 1 and sin 180 is 0. And if I'm taking it as 45 degrees, for example, then I'll be getting as okay. So now c1 is 0 here, we can get it. Now c1 plus c2 is 0, which means that c2 is also 0 because c1 is 0. Now c1 and c2 both are 0, then c3 also has to be 0, right, from this equation. So c1, c2, c3 all are 0, then it means they're independent. Fine. Okay, so one question, simple question, true or false question. Intersection of linearly independent set is independent. True or false? So you have an independent set, and the intersection you are seeing.
Yeah, it is true. Linearly independent it is.
Yeah, it will be true. So this is subset of any independent set will be independent, right? So if this is an independent set, then this is a subset of that. So this is going to be independent only. It's true for this also. So this is A, and this is C, and this is B. So A is independent, and C is subset of that. So C is going to be independent. Similarly, B is independent, and C is subset of that. So C is also going to be independent. So that's going to be true. Anyways. So okay, then union. What about the union? So if I'm saying that this is union, then cannot be, right? So you might have some common terms also in these two things. So if you have any common things in A and B, then you'll be getting okay, not like that. One second. Okay. Let's discuss this in detail later. Okay, take up this question. So find basis for a space of symmetric matrix, 3 by 3 matrix, such that Aij is equal to Aj. So what is the basis for this? So that will be simple. So you'll be having basis as one. This is the basis. This how to find this? So simple. Yeah. So for example, if you say that A, B, C, D, E, F, G, H, I like that. So if you have 3 by 3 matrix, then I gave it here that A, and so if it is B, then it's going to be B here, and if it is C, then it's going to be C here, and if it is F, it is going to be F here, and if it is I here, and it's going to be E here, right? So I can write like I have 1, 2, 3, 4, 5, 6, 6 different things. So I can write like this, right? So all these terms. So I'm not elaborating it, just a hint how to get it. Okay, now find the basis for each of these subspaces of the space P3 of cubic polynomial. Okay, so given the condition that P7 is equal to 0, and given the condition P7 is equal to 0, P5 is equal to 0, and P3 is equal to 0, and one more condition is P7 is equal to 0, P of 5 is equal to 0, P of 3 is equal to 0, and P of 1 is equal to 0. For these three conditions, let's find the basis for the cubic polynomial. So let's take up this question first. So P3 polynomial means what we know that P of P3 will be a0 plus a1x plus a2x square plus a3x cube, which will be equal to 0, and given that P of 7 is going to be 0, so you will get as a1 7 plus okay, let's write in a better way. So a0 plus, just substituting 7 in the place of x, a1x plus 49 a2 plus 343 a3 is equal to 0. So how can you write this? So a0 you can just write that this is try to write as 7a1 plus 49 a2 plus 343 a3. So this polynomial I can write as whatever term I have here plus a1x plus a2x square plus a3x cube. So I can write P3 as this. So okay, so minus 7a1 minus 49 a2 minus 343 a3, which I can write as a1 I can take in common, and it will be minus 7 plus x, and a2 I can write as minus 49 plus x square, and a3 I can write as minus 343 plus x cube, right? So this will be the basis. Dimension is 3. Okay, now for P of 7 is going to be 0, and P of 5 will be 0, and P of 3 will be 0. How can you get this? So P3, as we did before, a0 plus a1x plus a2x square plus a3x cube. So a0 plus 7a1 plus 49 a2 plus 343 a3 will be equal to 0. a0 plus 5a1 plus 25 a2 plus 125 a3 is equal to 0. a0 plus 3a1 plus 9a2 plus 27 a3, they will be equal to 0. Okay, now I want to find what is basis. So how can I do that? I want to find the relations of I want to find a0, a1, a2, a3 like that. So okay, so I can do like this. So it will be like 1 7 in a matrix form. It will be 343 and 1 5 25 125 1 3 9 27 a0, a1, a2, a3 will be equals to 0 0 0 0. So by doing elimination, Gauss elimination method, I'll do like row 3 will be going to row 3 minus row 1, as well as row 2 will go to row 2 minus row 1, which means I'll be getting 1 7 49 343 0 minus 2 minus 24 minus 280 0 minus 4 minus 40 minus 316. Okay, Now I will try to make this as 0. So you can see here that when row 3 goes to row 3 minus 2 into row 2, then you will be getting this will go to 0. So what will be getting? We'll be getting as 1, 7, 49, 343, 0, minus 2, minus 24, minus 280, 0, 0. We're getting 8 and 120. A0, A1, A2, A3 is equal to 0, 0, 0, 0. Okay, now beyond this I cannot reduce this, right? So below this I cannot reduce. So we have rank as 3. Now, but we have 4 variables. So we'll be having one arbitrary. Let's do the equations. A2 plus 120, A3 will be equal to 0. Minus 2 A1 minus 24 A2 minus 218 A3 is equal to 0. A0 plus 7 A1 plus 49 A2 plus 343 A3 will be equal to 0. Now from this I can say that A2 will be equals to minus 15 of A3, and similarly by back substitution I can get A1 as 71 A3 and A0 as, just by the back substitution, I'll just get A2 from here, from A2 as in terms of A3, so that I'll substitute here. So everything will be in A3, that will go on the right side, then you will get A0, A1 terms, and also similarly A1 and A0 terms. So A0 will be getting as minus 105 A3. So now what I can write, this polynomial I have A0 plus A1x plus A2x square plus A3x cube. How can I write like this? I can write as minus 105 A3 plus 71 A3 plus minus 15 of A3 x square plus A3 x cube. A3 is coming outside, so minus 105 plus 71x minus 15x square plus x cube. This is my basis. Dimension is 1. Clear? Yeah. Let's go to the next question. So I said that P of 7 is going to be 0 and P of 5 is going to be 0, P of 3 is going to be 0 and P of 1 is going to be 0 and polynomial P3. Okay, so A0 plus A1x plus A2x square plus A3x cube. Okay, so what will be the basis for this? So just think and tell me. So what does this actually mean? What is a 7? What is 7 here? 7 is a solution, right? 7, 5, 3, 0, everything is solution of, if I am saying that A0 plus A1x plus A2x square plus A3x cube as 0, then I am saying that P of 7 is 0, P of 5 is 0, P of 3 is 0, P of 1 is 0. Okay, so it means that these are solutions of that. Okay, so 7, 5, 3, 1 are solution of the polynomial P. Okay, right? Solution of polynomial P. Okay, yeah. So now I can write the polynomial this thing in the form of x minus 7, in the factors, right? Yeah. What is this giving? This is giving P4, right? But I said it's P3. But I am saying that it's P3, okay? I said P3 in the question, okay? Cubic polynomial, okay? So then, so basically from this condition we are getting that polynomial will be having degree 4, but we are in the space cubic polynomial space, right? So the only way in which P3 can be equals to P4 is only if it is zero polynomial. Okay, so this will be equal only if it is zero polynomial, but 0 is not a subspace, right? I mean, zero polynomial cannot be basis. Zero polynomial is not a basis, right? Why? Because basis means okay, so what is the basis? First of all, basis means with the linear combinations of that you will be able to get the span of the entire vector space. You will get the span. Okay, so by from the linear combinations. Okay, so but for if it is 0, then any scalar multiple of 0 will be equal to 0 only. So 0 can never be independent.
Yes, ma'am.
Because even if I am multiplying scalar, then I'm getting again the 0. So it should not happen like that. If I'm adding to 0 polynomials, I will be getting 0 only. So span means it has to be independent. Basis means it has to be independent. But 0 polynomial is never independent. Okay, so so this don't have any basis. So the basis is null set here. Is null set here, and dimension is 0. Okay. Okay. So next question. Find dimension of the vector space of matrices A, B, C, D. Okay. So what's that? A plus B plus C is equal to 0. A plus B minus C is equal to 0, and D is some polynomial. D is some real number. What is the dimension of the vector space of the matrices? So you have the conditions here that A plus B plus C is equal to 0, and A plus B minus C is equal to 0, which means that if I'm adding both, then I'm getting 2 of A plus B is equal to 0, which means that A is equal to minus B, which means that A, B, C, D can be written as minus B, B, C,
C will be 0.
and C will be 0, right? Yeah, if A plus B is 0, then if A plus B is 0, then
C is varying. C is free. C is varying.
C is varying, but if I'm saying that A plus B is 0, I'm getting, so A plus B is equal to 0 means this is 0 means
Yeah,
A
yeah.
plus B
A plus B 0 means C also 0. Yes, yes.
minus B, B 0, and D, so which means that B minus 1, 1, 0, 0, and plus D 0, 0, 0, 1. Okay, so dimension is 2, and bases are this. Okay, now tell me okay, so decide if this is basis of P2. Okay, so 3x square minus 1, 3x, x square minus x. Okay, so few questions. A, B, 1, x square minus x, C, x square plus x square minus x, and D, 2x square plus x plus 1, and 2x plus 1, and 2. So which one will be the basis of P2? first of all, what is the dimension of, okay, so let's see the solution. First of all, what is dimension of P2?
Three, one.
Yeah, so it's only 3, okay. So to show that, the hint I'm giving, so to show that the given set is linearly independent, then what we need to observe in this? Oh, I'm sorry, this is comma here.
NBC will be possible. Option C may be possible. Thus,
So even the
should be
independent
eliminated.
set, no, even this must have 3 members in this. So first of all, this has 4 members. Okay, so for this 3, for 3 we have 4 members here. Okay, so the 1, 2, 3, 4, right? So this won't be linearly independent set. And
So A and C, no chance.
no
A and
chance.
C.
And
Yeah.
this will definitely have. And you can see that you can just check whether this is independent or not. So C1 1 plus C2 into x square plus C3 into x square minus x equal to 0. Then you can just check whether C1 is equal to 0, C2 is equal to 0, and C3 is equal to 0 or not for getting this condition. So how can we do that? So C1 is equal to 0 and C2, okay, so I'll write this as C1 plus C2 plus C3. So C1 will be 0, C2 plus C3. Okay, so okay, so let's substitute some values and see in this. Suppose if x is equal to 0, then C1 is going to be 0, right? And if x is equal to 1, if x is equal to 1, then C1 is anyways equal to 0, and this will also be 0, right? So x square minus x term also will be equal to 0. So C2 also will become equal to 0. So now like this, these two are 0. So now this has to be, so this two are 0, C1 and C2. So this has to be 0 means C3 also has to be 0, right? So this will be independent. So like that you can check, okay? Okay, so the last question. Okay, let's take up the last question. Vector alpha 1, alpha 2, alpha 3 in R3 is a basis if and only if there is no plane through origin containing all vectors. So true or false?
I think it is true.
Yeah. So for example, if I'm taking ax plus ax plus by plus cz is equal to 0, and suppose if I'm taking x is equal to 0 and y is equal to 1, and if I'm taking some examples like that, so then I'll be getting as b plus into 0. And suppose if I'm taking x is equal to 1 and y is equal to 0, for example, then I'll be getting as write as so z I can write as minus b by c, and ax is equal to minus cz, which is ax is equal to minus c into z, which is ax is equal to b, x is equal to b by a, so x will be b by a, oh wait, sorry, so ax plus by plus cz is equal to 0, I can write as
Let's stick with standard basis. 1, 0, 0.
sorry, xyz is a plane, right? So xyz is a point in the plane, so xyz is equal to x, I'll write as b by a, y will be my y itself, and z will be my y will be some value. Okay, but better let's take with some number values. Okay, let's take with some proper plane. 2y plus 3z is equal to 0, for example, and if I'm taking x is equal to 0 and y is equal to 1, then I'll be getting as so for this I can write as 0, 1 and minus 2 by 3 basis, or else I can write like this. So my okay. Okay, let's simply say in this way. So if you have equation in this way, then if you want to write this, then simply x is equal to minus 3z minus 2y. So I can write as minus 3z minus 2y, and here I can write as y, and here I can write z, and which means that z is equal to minus 3, 0, 1, and y is equal to minus 2, 1, 0. So I have dimension as 2. So this is a vector this is a plane which is passing from 0 origin, okay. So in that case, I'm having dimension as 2, okay, but I said that I have vectors alpha 1, alpha 2 and alpha 3. Okay, so here dimension is 2, so the third vector will be definitely the dependent on the first two vectors, right? So this is going to be true, that you should not have a plane through the origin containing all the vectors. Is it okay? Maybe if you don't have a 0 here, maybe if you have some 1 or something here like this, then you will not be able to write. You'll be getting 3 bases, right? So I mean, you'll be getting dimension as 3. Yeah.
Ma'am.
So this is going to be true. Okay. So we missed out some 2 questions. I will look into it and post it in discussion forum, because now itself the time is 5:30. Yeah, is that okay? Is there any doubt so far? If you have any doubts, kindly ask me. Even that I will try to address in discussion forum. Yeah, so here we'll be ending the live sessions for basic linear algebra, and kindly if you have any questions, then kindly stay back, else we can end our thing.